So, hi again from my beautiful hotel room in Brussels, where I have nothing to do in my life than record more and more videos for your operating systems course, apparently. So, this is the video I promised that I will upload about the Linux kernel and development with the Linux kernel. If you have not yet downloaded the kernel, and if you have not yet gotten a development environment in front of you, then this video is not really as useful as I would hope it would be. And to view this video, the best way would be actually to have the kernel code somewhere accessible to you. So I know that I'm not expecting you to watch this at midnight, but if you can basically do it while at the labs or something, so that you can get access to the Linux kernel after basically downloading the Linux kernel, of course, and following the previous video. And of course, if you have access to a machine right now, then you can start playing with it right away. So let's start by saying what you guys should expect from this lecture, or I keep saying lecture, it's not a lecture, it's a video, of course. So this video will introduce us to some of the concepts and some of the things that are different between the coding style of C in Linux and the coding style of your day-to-day C. And what are some of these differences might be very subtle to you, but then you will get why they are very useful to know from the beginning when you start actually hacking into the kernel. So one thing to note on this topic that I mentioned in the first lecture is that, this is a very C heavy course, because the Linux kernel is basically mostly written in C code with some assembly, but it's almost exclusively C. And some of this is completely undocumented mumbo jumbo, but some of it is just very well documented, and we are going to hopefully try to catch up with the documented code, because it's much easier for you guys. But once you start with the documented code, it should be very simple to actually go on with the undocumented code afterwards. So this lecture sets you afoot on how different Linux is from your normal C code. Let's basically roll. So this is the source code tree, kind of. On the left hand side, these are the directories basically that you will find on when you download the Linux source, as described in my previous video. You will see these directories in your downloaded extracted file, if you don't, depending on how you download it, but you will probably get it from Git. And each directory has a set of files that are kind of related, but they might not be entirely related from one point, but they are very related from the other. So arc, which is our first directory, has the architecture specific source. Source here are basically the source files. And you know that, or if you do not know, then I should not assume things in the course, of course. So the Linux kernel can run on multiple processor designs and multiple processor architectures. And there are multiple processor architectures in the world. We know mostly of the x86, because this is what powers most of our computers. Basically our laptops, many of our laptops, not all of our laptops, some of our desktops, and so on. But there are also other architectures. There are even other producers that you might have heard of, like for example Spark, which was owned by Sun and now is owned by Oracle. And this is a processor architecture that is used mostly in server systems, but now also on mobile phones. You have things such as the ARM architecture, and the ARM architecture has multiple architectures. So there's the ARM64, there's the ARM, the normal ARM, which is the old ARM, and ARM64 is basically 64-bit processor. You have all of these variations. Even in x86 you have different variations, because we used to have processors where basically the register sizes were 32, but now they are 64, right? So I mean, all of these changes change the architecture. Also, within the same architecture family, you might find changes. So even between the Intel x86, let's call them the I generation, like the i3, i5, and i7, things that were produced before 2011, for example, supported different power management options than things that were produced later. So things that were produced after 2011 had what is called, for example, power capping, and the processors became much more efficient, or that they started having capabilities of that supports much better efficient power power consumption on your processor, basically in terms of the heat dissipated and so on and so forth. So there are a lot of these architectures, and Linux is pretty, as a kernel, it's pretty generic. It powers, well, most of our servers, it powers a lot of our laptops and of our computers at home, but it also powers things such as your mobile phones and your embedded systems. So Linux is actually used, I cannot say widely, but to a large extent in embedded systems, for example. So these kinds of things, these architecture-specific code that are optimizations, for example, if we look at the x86 and power capping, which is a new feature that was added after 2011, then the Linux kernel that works, I mean, the same Linux can work on both architectures, on both processors. But you have architecture-specific code that basically enables the more advanced power management options, for example. And then you have the block directory, and it's basically the second directory on my list, which basically has the block IO layer. And we'll talk about block IO in a bit more details, but this is basically what manages well, your hard disks, okay? And well, there are differences there. Then you have the crypto API, and well, this is not core Linux, right? But as we will discuss later, it needs to be implemented in the kernel, or to be part of the kernel, so that when the kernel needs some cryptographic functions, then it can basically call them, because the kernel is the absolute truth, right? I mean, you're not in the kernel, you cannot in the kernel go and basically download a new library and add it to your kernel, which is sort of what you would do in your Java code. I mean, if you want to do some cryptographic work in Java, you basically go through the internet and you find that there is a library that's called Java Crypto or Crypto Java, I cannot remember, I'm not a Java guy, and then you download that and you include it in your source code. But now the Linux is not like that, the kernel is not like that. So the kernel needs to take care of everything that it actually needs. Then there is a huge folder that is called documentation, and the documentation tries to document both Linux concepts. So you'll actually find in this documentation that this is a huge book. These are volumes and volumes probably of text, and they try to describe into as much details as possible how things work internally. But they are very disorganized in many ways, but we'll still use them. This is a very valuable resource for you as a Linux kernel hacker. You just go there and you find different folders that contain basically different descriptions of, for example, different parts of the Linux different subsystems, for example. Also, I mean, we will use this. We will use it through the course, so do know it. And then you have the drivers folder, and as we said in the first lecture, probably in the second lecture also, that well, when you when you basically buy a new Linux, when you buy a new Microsoft mouse, there are no Linux mice, unfortunately, and mouse with an S, not with a TH, of course. So when you buy a new Linux mouse, you basically do not want to rewrite your kernel because, oh, I'm just gonna plug this small mouse that has all these new features. So I actually have a mouse, an ergonomic mouse that comes with 15 keys, and I don't even use them. But I mean, if you have this new mouse, well, or if you have your new very fancy gaming device, like your, for example, I mean the gaming stuff that people use. I mean, there are things like the driving wheels that you, if you're playing Need for Speed, I'm that old, I don't know if they have new versions of that, but anyway, if you're playing Need for Speed, there used to be this well, gaming driving wheel that you can buy and plug it into your computer and just like feel, I don't know what, but basically, yeah, give you some control. So if you're buying this, you do not want to rewrite your kernel, right? So what you want is that you want something to be pluggable, just something you put in the kernel, and then things should work out of heaven, basically. And these are basically your drivers. And the drivers control almost every part of your peripherals. So you need drivers for pretty much everything that is not your processor, and a few other things like your memory also. But you even need memory drivers also. But so drivers are everywhere. This is where you specify vendor-specific stuff that are not generic, that cannot be generalized, basically. There is also the firmware, which is tightly coupled to the drivers and what they contain, and then you have these are device firmwares needed to use certain drivers, and these two contain a hell lot of assembly code also. So I mean, it's not just C code here. Then there's the VFS file system and other individual file systems, and we are going to talk in quite a bit of details on the file system in Linux later also. Then you have the includes folder. I hope that my breathing is not as bad, but I just need to catch my breath. So then you have the includes folder, which basically contains all the kernel headers, and well, these are C headers. If you don't know C, then well, you have some time to learn C in this course, but it will not be the funnest course in your life. So it's basically the kernel headers, the C headers .h files. And then you have the init, which is basically the kernel boot and initialization code. It goes over here. We actually talked a bit about this to some extent. We have not really gone into details into this. Then you have the IPC, which is the inter-process communication code. That basically manages how different processes can talk to each other. And then there's the kernel, the core subsystems such as the scheduler. And this is also where we will spend quite a bit of time in this course. So now you have also the lib folder, which contains all the helper routines. Okay. And it contains all the helper routines that you would, that the different parts of the kernel would actually require to do stuff. So, then you have the MM folder, which has the memory management parts, the memory management subsystem and well, the virtual machine subsystem of Linux, how Linux manages virtual machines also. We will also talk quite a bit about this. And then the net folder, which has the networking subsystem, samples, which basically contains some sample and demonstrative code. You can actually take a look at this right away, because this is, well, sample code. What can you expect in sample code? Then you have the scripts, and well, these are the scripts that are used to build the kernel. I mean, you build the kernel on operating system, right? And you need some scripts to do that, and these are basically these scripts. Then you have the security folder, which contains the Linux security module, and this is not to be confused with the crypto folder. The crypto folder just implements cryptographic algorithms, while the security folder actually provides Linux the other parts of the security. Then you have the sound subsystem, which is, well, you have the sound subsystem over here, and that's a big thing also in Linux. Then you have the user space code, that is in USR. You have some tools that are helpful for writing Linux. You can actually look at these for at this folder also for tools that can help you to basically have a working dev environment. That's another option from the options that I basically had in the previous video. And then you have Virt, which is your virtualization infrastructure. This folder basically has all things about virtualization that is not related to the memory management of the virtual machine. Okay, the Linux kernel versus C kernel applications coding. And basically Linux uses GNU-C, and that's a bit different from ANSI C. It's not entirely different, so it's almost the same, but I mean there are subtle differences that Linux makes use of. And if you are an ANSI C guy, well, you probably are not, but just in case that you are an ANSI C guy, this should not hinder you. I mean, it's not like two different languages or anything. It's just that you have some new constructs or some different constructs or some different usage of things. So that's one of the first major differences. The second major difference that I would say is that the kernel has no access to the C library. So everything that you need is actually implemented inside Linux. And by that I mean, since, as I said, well, Linux is the absolute truth now. It actually runs on the core kernel. It does not have the luxury of including things from the C library. It also does not have the luxury as being a kernel that aims to have as minimal footprint as possible. Does not also have the luxury of basically importing all of the C library or the standard C headers, because that would increase its memory footprint considerably. It will make it use more resources, and no, we do not want that. So the way that Linux does it is that everything that you need gets implemented. And if you go here, that's basically you're in your /include folder. You'll find a lot of these implementations, or actually the headers to the implementations. Then you have the point that the kernel lacks traditional memory protection that the user gets. So if you're in kernel mode, if you're the kernel developer, then the kernel basically has no one to check after it on what is happening. So if you mess up the memory, you can actually mess up your memory pretty badly. You can mess up applications. You can even make applications unusable because you just messed up their code in a way that, well, doesn't help to try to fix it in any way. So, except if you, of course, go and reinstall or something. And you can mess up your kernel itself. So you can actually, if you're not careful enough when coding the kernel, then you can actually mess that up pretty badly and destroy your kernel, basically. One thing to note is that the kernel has no easy way to implement floating point operations, and we'll discuss that in a bit more details in just a few minutes. And that the stack of the kernel is fixed and it does not change. The size of the stack should not change versus the stack of a normal application, which can change. The kernel has asynchronous interrupts. We have actually talked about that. So we talked about the timer interrupts that can just happen out of the blue, and then your application will just, or your process will just stop until it's basically rescheduled on the CPU again. And that basically means that you can never assume anything on how synchronous is the system, on how does things happen with respect to time. And that basically means that synchronization and concurrency becomes a major nightmare, especially if you're on a multi-process test, a multi-processor application, multi-processor processor, sorry. No, that's even more stupid. Multi-core processor, sorry. So, if you're having a multi-core processor, then synchronization and concurrency are major concerns, because well, when you're preempting some of the threads or some of the processes which owns some data, there might be another process running on another core that is accessing the same amount of data, and that might just cause issues. And we are going to actually have a bit of fun on this. And there is portability, of course, and portability is very important. So keep all your architecture dependent or device dependent code in the respective folders, and do not mix things together. And that way, you basically make sure that whatever you add to Linux does not mess up whatever Linux already had. And now we are going to go through the points that I just mentioned in a bit more details, starting with the fact that, well, you have no standard C library and standard headers. And basically, the way that Linux does it, as I said, is that by re-implementing most of these functions that you would need. So, for example, the standard, or not the standard, but rather the common string manipulation functions are in /lib/string.c. And well, slash here is not your home slash, is not your root slash, but rather the Linux kernel slash. So when you go to you download the source code, take that source code, and you will find the tree structure that we just mentioned. And in this tree structure, you'll find the lib/string.c. And then there are other, so for example, architecture specific header files that are located in this folder, which, well, as anything that is architectural dependent is what you'll find in /arc. Then /arc, for example, /arm64/include will have all the includes that you would need for an architectural dependent functions. So one thing that you're going to miss is your printf statement that no longer exists, and Linux implements printf into printk instead. And well, printk is kind of your best friend in debugging. That is basically how you do debugging in most of the kernel code. You basically suspect that there is a problem, and as we said during the lecture, that we are going to do a lot of debugging in this course. So you suspect that there is a problem in some parts of the core of your code, and you go and add printk statements. And printk statements are a bit different from printf statements because they allow you to set something that is called a priority flag, and that's basically what is the severity of the error. So if you have been using, for example, Java logger or some logger library, you might know that you can have several levels for your logging. So you can have something that is like info, something that is severe, and so on. This is kind of the same where you have basically the printk printing kernel error, which basically means, oh, this is complete crap. But there are different priority flags, and you can actually, using the priority flags, set where these print lines go to, because you don't want all of them basically blowing up in your face. And do note that there is no comma here, right? This is a flag. This is not something that you add to the code. This is just a flag. Okay, and this is actually an example from the file hibernate.c, which is basically used for you to hibernate your computer. And you can see that in this example, you can see that some devices failed to power down, and that basically means that your system cannot hibernate. So this is actually the hibernation code that is used on your computer. When you hibernate, this is the file that actually hibernates your computer, and this is what happens if you get an error in your hibernation. You basically try to read if there is any errors, and if you find an error, then you basically get that. And well, this is a function, of course, that returns either null or something else, but I mean, you can just go and if you have the environment, you can just easily on Eclipse press F3 on this to basically jump to where this function is implemented and keep jumping back into your code until you basically understand it. But this is basically what your kernel will typically throw at you if some of your devices have failed to hibernate, and well, sometimes this is just because you're doing something that is weird with your devices. You might have seen that message actually a couple of times. I don't know. I have actually. So that's just an example. Then let's look a bit more on what GNU-C is. Well, you might have used GCC. Well, this is standard GNU-C, and if you do not know the difference between the C versions, then these are two Stack Overflow, or this is one Stack Overflow question that basically points you to the difference between C99, ANSI-C, and GNU-C. And this is also on one of the forums for Linux questions. It's called linuxquestions.org, where you can basically see that people are trying to differentiate between GNU-C and ANSI-C. And now we are going actually to go a bit more into the different details that the Linux kernel actually uses from GNU-C that you might not be very familiar with. Actually, some of them made them to the main C, the standard C that everybody uses now, but some of them did not. So starting with inline functions, and inline functions are basically a way to optimize your code, to instruct your compiler to optimize your code in a better way. And this is a really nice description of what an inline function is. And it is basically something that you instruct the compiler that instead of the compiler basically jumping from doing a branch and going to that function code, which can lie in a different memory location, to instead copy the function code and replace your code with this code. So it's kind of you basically instructing the compiler to go fetch the code and put it here. This has a lot of nice effects on your speed, because it's actually faster than basically jumping to a different memory and context switching and so on. And you no longer need the call and return sequence, but you're rather going in the code sequentially. It's just a way to make it shorter in the middle, especially if you're using it multiple times in the same file or something. But then it has also a very bad side effect, which is basically that your memory footprint grows enormously. Because what you're doing is that if that function is, suppose, 5,000 lines of code, and some functions are, well, not 5,000, but maybe a few hundred lines of code, let's say, then you're basically copying all of this into your code in different parts. And if you do that 100 times, then you have just increased your size by 100 times the number of the function size. So this bad side effect can actually affect your memory footprint. So there is a trade-off, as with everything. And this is an example of how inline is used in basically the high resolution timer file in Linux. And high resolution timer is basically a timer that, well, has a higher resolution than what Linux originally had on a nanosecond granularity. And this is actually how they get the high resolution. It's in this file, basically ktime.h, that you find many of these, and this is one of the inline functions, and this is the description of the function and what it actually does. It actually takes as input the seconds or nanoseconds to set, and then gives you a ktime t representation of the value, which is some representation in Linux. Then inline can actually use for assembly. We will not see a lot of assembly in this course. We will actually try our best to avoid assembly because, well, assembly gets you locked in. But it's also worth seeing some of the assembly code that is out there. So this is actually the assembly code to transfer you to the protected mode. And that's basically by clear, you can see here, for example, that this call assembly volatile is calling CLI, which is basically an x86, means clear interrupt flag. So this is the x86 code. This is the real code that is used on x86 machines. So where do you think that will be? And now, knowing that this is in /arc, then this is the x86 code for changing to protected mode in your kernel. Okay, and well, these are actually also assembly calls to do different things related to the boot parameters. It actually checks if you support some mode, and if you do not, then you go into that and you just clear the interrupt flag, which is basically stop all interrupts from occurring and going to do something that is kind of dangerous to have it interrupted. And then one more code optimization that we have and that is highly used by the Linux kernel is the likely and unlikely built-in directives. And these are actually meant also again to optimize the way that the compiler runs. It actually tells the compiler that if you put likely, tells the compiler that it's highly likely that this is going to happen. So basically, you can go and fetch this code from memory. If you basically say it's unlikely, then you're basically instructing again the compiler to basically say that this part of the code is a corner case. It's rare to happen, but it might happen maybe once every 10 years, maybe once every hour, maybe once every minute, because a minute for a CPU is quite a long period of time. So when you mark something as unlikely, you are telling the compiler that this is probably not going to happen. And then this has a cost. Can you think of the cost that occurs when using likely or unlikely? And now this is actually how we use them. So this is basically if unlikely error, that's your directive, and if likely success, that's your directive. So how are these used in real life? This is actually the code that is used basically for some parts of the Linux scheduling, and it's in a file that's called workq.c. It's in the kernel folder, in the scheduler folder, or not in the scheduler folder. I think it's just in the kernel folder. But yeah, regardless, I mean, you will find your way through the Linux code. It's just a matter of you searching. And you can see here that again, you basically are, for example, if you have a workers list, which basically means a list of processes that are waiting to run in your system, you basically try to get one of them, and if you cannot get one of them, then I mean it's unlikely that you do that and then you return with null, because usually you have something to do. If your computer does not have something to do, that's basically when you have gone to sleep and left your computer, or left your work and left your computer, and then it will go in this once, and well, it will just sleep, because most computers now can sleep pretty efficiently and will not hit that part of the code a lot. And also, since well, basically this is going to only hurt performance when the computer is actually idle, it has nothing to do. So I mean, sorry. Performance cost that you lose over here by having this as unlikely is not going to hurt your running performance at all, right? And this is also another use where you basically are using likely, or the kernel has the term likely, and that's basically the function to wake up a worker, wake up some idle worker, which is basically waking up something that is sleeping right now, some process or something. We're going to talk about what workers are in a bit more details, but think of them right now as processes. And you can see that, well, if likely work, I mean, you try to fetch a worker, you try to fetch the first idle worker from a pool, and you set it here, and well, it's very likely that you find an idle worker, because, well, it's very likely both that you have things to do, and since you have things to do, you have things that are idle, waiting for processor time, right? So this is very likely to happen. Then one more thing that the Linux kernel has is that no memory protection, as we said. And basically what happens when you violate, when you're in user space and you violate the memory rules that are put, then the kernel traps the error, catches the error, and sends a segv signal, and basically kills the process. So if a process is malicious or is buggy or just went banana and tries to touch the memory of another process, the kernel will just kill it. But when the kernel attempts an illegal memory access, then this is a real problem. You get whoops, and it is actually called whoops. I mean, I'm not making this up. The kernel error is called whoops, and this is one of the worst kernel errors that you can get. And let's look at the code that actually runs when basically you try to access some page that was not present. Basically, the kernel tries to access some memory page. We'll talk about memory pages later. I know that you probably don't know what memory pages are, but think of them as some part of the memory that is not there. Well, it was deleted, it got corrupted or something. So the kernel tries to access some page that was not present. And basically what happens here is that, well, are we prepared to handle this kernel fault? It might be the case that yes, we are prepared to handle this kernel fault by using something, well, intelligent, or we know that if this memory page is not there, then we can do something. If we cannot find a handler, then we are kind of screwed, right? So you basically find that here no handler will have to terminate things with extreme prejudice, and you basically start whoopsing. You go into whoops mode, and that's basically die whoops regs ESR. Okay, so this is your whoops, and this is basically you trying to access a memory page that was not present. And you can search your, again, Linux kernel for fault.c and check the lines in your code that I hope you will have by now on your machine. Then we have talked about floating point operations. We actually mentioned that a bit during the first lecture. Well, you should never ever try to do floating point operations in the kernel. It's always a horrible idea. I mean, it's almost never a good idea to try doing a floating point operation in your kernel. And if you're new to kernel development, just thinking about it means that you are probably wrong. I'm not saying you're entirely wrong, but you're probably wrong there. Floating point operations, the way they work in user space is that the kernel catches a trap or syscall and then initiates the transition from integer to floating point mode. And this transition is actually very architecture dependent, because some processors, they have floating point operations supported, some of them do not, and I mean, it's very architecture dependent. But basically the way it works is that it's code from user space, and it initiates some transition that then basically the kernel initiates some transition that are very architecture dependent. Well, inside the kernel, it's really hard to actually have this trapping mechanism or system call mechanism inside the kernel. So what you need to do if you're going to do a floating point operation inside the kernel is that you're manually going to save and restore floating point registers and deal with the whole idea of switching to floating point mode by hand, basically. And this is not a really nice thing. It's actually highly tied also into the assembly code of the architecture. So you will need to do that by also doing quite a bit of assembly code. So we have also talked about that the Linux kernel stack size should be small and fixed, and we are going to go into quite a bit more details into the kernel stack size in a while in the course. So this actually concludes what I wanted to say today, and that was basically a quick intro to what your Linux might be different from your normal development environment, what you would like to get a bit more accustomed with, and also will give you some code snippets from actual Linux kernel code, and hopefully give you some ideas, or get you heated to what lies ahead, which is hopefully fun. So with this, I conclude, and I hope that you have a very good night and or a very good morning. You probably are going to see this in the morning, and well, see you on Friday. And the actual next lecture is going to be also posted, not today, but tomorrow night. I will post the new lecture from the course. Thank you.